Hello, everybody. Welcome back. I'm going to pick up where we left off last time. Today, we're going to take that result and finally recover the parton density expressions that you will find stated often without any comment in papers or even textbooks. But again, we need to start with the last equation from last time. If you recall, here's what it was. This was our second definition that we're working with, so I put a 2 subscript there. The first thing that we're going to do is take a few more steps to refine the expression of this equation still further. It'll just be a little bit useful. It might be worth pausing and noticing some aspects of this expression. For example, notice that it's not Lorentz invariant, right? We've got particular component of the form momentum to energy, particular pulled out here. The reason for that is that we've defined this density as a momentum fraction. Remember, I put this EP in here, but it was a momentum fraction relative to the energy of, it was the fraction of momentum relative to the energy of the target proton or target hadron, rather than with respect to the energy of the parton itself. So if I made this EK rather than EP, we get something Lorentz invariant. So we have something that's not Lorentz invariant. That's okay. It just means that we need to specify which frame we're defining this parton density in. We need to pin it to a particular reference frame. And we'll do that here in a second. First, let's try to convert as much as we can to light cone variables, plus and minus component variables. And also we can get rid of these gamma zeros. That'll be useful here in a second. So the first thing is to note that the energy, in general, the energy of a particle times square root of 2 is equal to the sum of the plus and minus components, just following from the definitions. If there's anything here that isn't immediately obvious, maybe pause and check for yourself. The other thing I'm going to do is I'm going to define another form momentum that's K with an underline on it, which is the original K, but with minus signs on all the 3 momentum components, as I've written it here. Then what you can fairly easily check is that gamma 0, K slash gamma 0, just gives back this K slash with the underline on it. It just flips the sign on the 3 momentum components. And then what does it mean in light cone variables if you switch the sign on the 3 momentum components? Well, you switch the sign on the Z component, that just means that you flip the plus component to minus component and minus component to the plus component, right? Because the plus component involves energy plus Z component, the minus component involves energy minus Z component. So you just flip the signs on the Z components, you're switching minus to plus, plus to minus. And the transverse component also gets a change in sign. So if I write out the K underline slash, I get, of course, from the definition of, well, from the way dot products work in light cone variables, I get this first line here, but then K underline minus is just K plus, and K underline plus is just K minus. So the expansion is actually like this. So to check that, you can do the following. Well, gamma minus is defined in the same way you would define any light cone variable. It would be the 0 component minus the Z component. And if I apply gamma 0, well, gamma 0 squared is always 1, right? So let's just look at the sandwiching of the gamma zeros around the gamma Z. And if I do that, I use the Dirac representation of the Dirac algebra for gamma Z. And gamma 0 is just the diagonal entries with a minus sign here. And write that out, and I get negative gamma Z. So it's just flip the sign on gamma Z. And you can check similar relations for the X and y components. They both give minus signs as well. And so if I do the gamma 0 sandwiching a slashed momentum like this, all I do is switch the signs on the gamma z, the gamma x, and the gamma y. So I get what I just said up here. Okay, why have I done this? Because I just want to simplify this factor here. And if I apply what I just said, then that factor becomes, well, gamma 0 squared again is just 1. So it just means that I put an underline on the gamma slash and remove the gamma zeros. Okay, so that's one simplification. Well, that's the second simplification. The first is that I can write the energy as k plus k minus, for reasons that become clear in a second. So I'm just rewriting that expression again the way I have it here. Okay, now I just said that we need to define this relative to a particular reference frame. Really, it's at this point that we need to think very carefully about how we actually are going to use a parton density. Okay. Well, first of all, we're thinking about collisions of particles at very high energy. So usually we're going to have this hadron, this proton or whatever, moving at a very high speed relative to something else, probably one of our measuring instruments. So we probably want to define this in a frame where the proton is moving very quickly, moving at a high speed. Maybe not actually infinitely, but moving at a very, very close to the speed of light rapidity. So maybe not infinitely, but nearly infinitely moving frame. And how is it that we actually use densities? This is a density, literally, right? It's partons per unit of volume. So the way we use a density when we're applying it to something, anything, is that we integrate it over something, right? It's partons per unit of volume of momentum space. So for momentum space, so we need to integrate over some region of four momentum space with something else. And usually that something else will involve, well, will be representative of how we're doing a particular type of measurement or observation. So I'm going to express that here, and the details here don't matter. I'm just trying to be as general as possible. We're going to say integrate this density F2 with something that I'm calling capital T here in blue to emphasize it. And then, of course, this momentum will be dotted, there will be some Lorentz invariant forward vector dot product with whatever other momentum might be involved, which I've represented here as L, but there could be many other momenta involved. Remember, I'm trying to make this, again, as general as possible. So there's a function of a bunch of external form momenta dotted into K, our parton momentum, and multiplied by the parton density that we've defined so far, and integrated over the forward volume. Okay, now I've put out here an explicit 1/square root of 2 times EP, because remember how this density was defined. It's dn per unit of this stuff. So the plus component is represented by the x, which is k plus over square root 2 EP, if you recall back here from the last lecture. And so I've just pulled that out. That's all that is. Okay, and what we want to say is we're going to do this, but in a frame where, well, let's say T is describing operations that take place in some lab rest frame, and the proton or the hadron is moving through very fast, very rapidly, near the speed of light. Now there's a set of simplifications, important simplifications and approximations that we can make. And that's what we're going to talk about here. So what are these simplifications? Now, the approximations are not completely obvious, and it helps to try to be as visual as possible, to try to visualize what's happening with these kind of collisions that we're thinking about. So with that in mind, let's actually try to think about what happens in the rest frame of the proton of the hadron, target hadron. I know I said we're going to ultimately think about it in the frame where it's moving very quickly, but let's step back and think about it in its own rest frame for just a second. And this kind of a picture I like to draw, Minkowski diagram picture I like to draw. And I made a fuzzy red path showing the trajectory of the proton in its rest frame. And it's fuzzy because it's made out of partons, quarks, and so on that are not completely localized. They're sort of spread out, at least to some extent. The green line is, say, some kind of observer, maybe me, moving very rapidly in the minus direction. Okay, so the observer is moving at nearly the speed of light in the minus z direction. Of course, there's an x and y component as well. And the way things spread out in the x and y components for the proton is similar to the way they've spread out here for the z component. We can't really draw the x and y components, but you can try to imagine them maybe being perpendicular to the screen. And okay, what do we see? Well, if the partons are, well, they're not going to be completely spread out because we've got a localized object, but if they're spread out enough, then we can say that the 3 momentum is going to be localized to a reasonably quote unquote small range. Now we have to think small relative to what, but it's going to be something with an upper bound. Let's say that, well, we're still talking about a free field theory where we're constructing these states out of wave packets. We can say, let's make the states strongly suppress very large kz above some size. You might go back and think about our discussion of Feynman's lecture, where he talks about the hypothesis that momentum above a certain level are not important. Those types of ideas start to become relevant here. And so kz, kx, ky, they're all going to be bounded in the rest frame of the proton to be below some level. And the reason that I'm saying that is because now we can imagine, what do those partons look like if we view the proton instead in a boosted frame where now me, the observer, is at rest. So I'm going along this green blob in the vertical direction. I'm not moving. And it's the proton that is moving very fast. Well, if I'm boosting in the z direction, the transverse components don't change. But now the z components get very large. Remember, there's a spread of z components that's restricted to a certain region. And so what happens now is that the plus component is going to be a spread of values restricted to a certain region, whereas the minus component is going to get small. So maybe think about that for a second. I'll try to make a few more comments to help you here in a second. Actually, the easiest approximation that you can see is what happens with the components of the proton's momentum in light cone variables. Okay, if the proton as a whole now is moving very rapidly in the z direction, its z momentum is very large. Okay, the plus component is energy plus z component divided by √2. And so the plus component is going to infinity as we imagine this proton going closer and closer to the speed of light. Remember that the minus component, if the proton has a mass m, and we define the axes so that it's moving along the z direction, so there's no transverse component. If it's got a mass m, then the minus component looks like this. And so as we go closer and closer to the speed of light, the minus component goes to 0, and quite rapidly, right? It's m squared over, it's 2 factors of p plus smaller than the plus component. So to an observer like me traveling along this green blob, I'm very justified in making approximations to the proton where I just keep its plus component and drop its minus component. That means that, well, EP, remember EP is P plus P minus over root 2. So square root of 2 times EP just becomes a P plus. So that's a nice simplification. One thing it means is that this momentum fraction that I defined in the last lecture, x equal to k plus over 2 root EP, just becomes k plus over p plus. It's a light cone momentum fraction now. Okay, so now we're talking about the L rest frame. L was, if you recall my schematic notation back here, L was one of the momenta associated with the rest frame. So something not too large relative to the observer's rest frame. So we can call this the observer's frame. Observer's frame. Okay, and since the Z components of the constituent partons are restricted by the wave function to lie within a narrow, reasonably narrow band, then a similar type of set of approximations apply to the actual components of K, the partons components in light cone variables. So remember, we can express each of the light cone components of K in this way, K plus, and we're saying that all the partons are free on-shell partons, so they all obey K squared equal to MQ squared. MQ is the mass I'm giving to these particles. And we have a similar thing to what we had for the proton, except now we'll allow for some transverse momentum. And if we're boosting from the previous page back here, then K plus is getting close to infinity as we boost from this picture to this picture. And so what do we have? We've got K plus going to infinity. So that means that the first light cone component, K plus, is 1 power of infinity larger than K per, and 2 powers of infinity larger than K minus, because K minus has these fixed momentum and energy and mass scales squared divided by K plus. So as K plus goes to infinity, we get a relative power situation schematically represented by these light cone variables. And so again, I'm going to say, let's just keep the K plus. Okay, so how might this be useful? Remember that my definition had this K plus K minus in denominator over here. Well, if the wave function of the hadron is keeping all the K pluses to be close to infinity and K minus to be essentially negligible, then we can just say the K minus is 0 and write K plus K minus becomes K plus. And we'll drop these corrections that go to 0 very quickly as K plus goes to infinity, as we boost to a frame where the proton is moving very quickly along the Z direction. Similarly, remember this expression that we got where we had K slash underline. Okay. So now I'm looking at this piece of our previous expression, this K underline slash plus MQ. Okay, it's K plus gamma plus K minus gamma minus and K per gamma T. And again, it's the K plus that dominates completely over the other terms in this expansion. Okay, so I can just keep the K plus gamma plus. So we can make these substitutions inside of our definition to get basically our final definition for Parton density. Since this is a little bit of a slippery argument, let's make sure that that makes a lot of sense. I'm just going to return to the page where we left off, where I was discussing how we utilize these densities. Remember, we have to take some integration. So how can we justify these approximations? Well, if we're in the frame corresponding to this, where the proton is moving very quickly, and here at the origin is where the proton intersects with me, the observer. So the T is describing whatever operations take place right here. And what we're saying is that, assuming that we've got a reasonable state for the proton, I mean, reasonable meaning it models what we expect for the proton, it restricts the momenta to be within a certain range, then this integrand in the reference frame that we're looking is going to be very restricted to the part of the integrand where k plus is close to infinity, k perp is 1 power of infinity smaller, and k minus is actually 2 powers of infinity smaller than that. And this overall 1 over root 2 EP just becomes 1 over P plus. So I can make those replacements from the previous page, the ones down here in particular, inside of F2, and the integral won't be modified. So let me do that. Let me take that F2 that we ended with in the last lecture and replace K underline slash plus NQ with just K plus gamma plus. And let me drop the K minus here. So I just have a K plus downstairs. Of course, the K plus here cancels out the K plus here. And anything left over is going to be basically 1 power, quote unquote, 1 power of infinity smaller than what I have here in this boosted frame. Okay, so this is essentially, I know I keep saying that we're essentially at the end, but really we're getting very close now. This is essentially the final definition with a few more steps to go, but we're basically there. I've just taken F2 and done these replacements, and what I've done is I've removed the 2 subscript, no 2 subscript. And the fact that I haven't added a 3 subscript should tell you that we're pretty much there. We're pretty much done, so keeping subscripts no longer is really helpful for us. And now X, remember, I previously defined it as K plus over 2, or square root 2 EP, but in this infinitely boosted approximation, it just becomes K plus over P plus, so it's really a light cone momentum fraction. And this is the expression. Now, several comments. It's a parton density still in all 4 components of 4 momentum. For this free field theory case, that's a little bit trivial because we know that the 0th component will always have a bunch of delta functions that force it to obey the relativistic dispersion relation. Well, in fact, you might have noticed that in high energy physics or nuclear physics applications, you don't generally see that as the parton density. On the other hand, I wanted to pause here and say you can imagine that something like this might be useful. And in fact, we call this the fully unintegrated parton density. I think there are various words for it, but that's what I've called it basically in the past, because there's no integration over any of the components. All 4 are there. And you could imagine applications where that might be useful. It basically means that it would be useful if you need to have sensitivity to all 4 components of a parton's momentum, of a parton's 4 momentum. The plus, minus, and the perpendicular, even though the minus is very, very small. Okay, but we can do a few more approximations that simplify it even further. And as usual, we'll go back and think about how we use parton densities. So I go back to this kind of integral. What I've done is we started with this operation, the integrate with a fully unintegrated parton density, in our definition with the 2 subscript. Now we're saying, look in the highly boosted reference frame, and up to terms that are going to 0 as we go to more and more to the boosted frame, we ended up with this expression where I just made the substitution, and I've dropped node to subscript. I've dropped the subscript, so it's the definition from the previous page. Okay. And the dk plus or p plus is now just dx. Okay. And here I've just basically copied and pasted this fully unintegrated parton density definition, but I've expanded out the terms in the Fourier transform exponential because we're going to use that here in a second. Note that sidebar, depends on the coordinate in 4 dimensions, y, and it depends on all components because this is still, like I just called it, the 4-dimensional fully unintegrated definition. And if you want to see discussions of how this kind of fully unintegrated definition might be useful in applications, or has been speculated that it might be useful, I've got some of my own work from 2008 that you can check out, but I only list that there to emphasize that we're getting to parton densities definitions that are actually used in some capacity. Okay, but going back to how we can simplify it, we said that K is basically going like a plus component that is like infinity, a minus component that is something fixed over infinity, and a perp component that is something that is fixed. Okay, so what that's telling us is that the minus component is getting very, very small. It's very, very small over the range of integration that we're dealing with here. Okay, so if we imagine a t that you might have in the real world, that's representing some kind of observation or measurement number. And so there's a good chance that we'll have essentially no sensitivity, no practical sensitivity to that minus component. We just don't have enough precision to be sensitive to it. Okay, and that's actually a good thing because being sensitive to the size of masses brings in a lot of complicated dynamics. So we might want to just ignore the minus component inside of T and take K to just have a plus and perpendicular component and assume that we've just averaged over all possible small minus components. So what happens if we do that kind of approximation? So here I'm just stating what I just said. What if I have no sensitivity to this minus component that is going to 0 so quickly as K plus is getting large? Well, I'm going to say, let's remove any sensitivity to the minus component. We'll approximately remove any sensitivity to the minus component inside of capital T. No K minus. When I dot with L and so on. That means I'm taking the 4 momentum K and changing it into an approximate 4 momentum where I'm assuming that I'm averaging over all the, I'm averaging over all the minus components. And then if there's no K minus in here, then when I do this integral, the integration only acts on the f. This integral then only acts on the f. So I put it here separated into brackets. To see how this works in a little bit more detail, remember I had specified an L earlier to represent a typical momentum inside T. And you're going to have dot products like K times L. Okay. So if all the components of L are basically small and fixed, then again, it's only going to be the K plus times the L minus that really matters. Okay. Well, what this means is that I can just look at this object as its own parton density. I just take f from up here, integrate it over all k minus. So what happens when I integrate over k minus? It just acts on this part where there's a k minus. It turns this part of the exponential into a delta function that sets y plus equal to 0 when I integrate over the y plus component here, right here, and gives me another factor of 2 pi. So all that happens when I integrate over k minus is I get rid of the integral over y plus up here. I get rid of 2 pi in the denominator here, and I set y plus equal to 0 everywhere else. So let's go ahead and do that. When I do the integral over k minus, now I get a function that is no longer depending on k minus, so it just depends on the light cone momentum fraction in k perp. And now the integral that was previously over all 4 components of y has become an integral only over y minus and the perpendicular components of y. And the y plus has been set equal to 0. So I'm writing out each component of psi bar now here and explicitly indicating that y plus has been set equal to 0. And this is a function, again, now of the longitudinal momentum fraction x and the transverse momentum. So you might have seen this definition before. This is a standard type of parton density that is very often discussed and used now, called a transverse momentum dependent parton density, or TMD-PDF. If you want to see a textbook expression of it, I reference column 6.79 here for you to look up. It's also sometimes called an unintegrated parton density, as opposed to fully unintegrated, because it's still integrated over the minus component. Okay, the transverse momentum dependence, of course, is referencing this transverse momentum argument. Well, of course, we can go further than this because the transverse components are also small relative to the plus component. What I just wrote back here was that the transverse components are remaining fixed as the plus components are going to infinity as we look into this boosted reference frame more and more. So back here, we could also say, or let me write it down here. We could also say, what if the t that I'm using is also insensitive to the transverse components, which again will often be the case. Not always, but often. Then I can approximate the k one more time. In that situation, I can say k only has a plus direction. This is starting to look like our discussions of the parton model. We were saying that a proton is coming in. If it's moving very fast, then it only has components in the direction of its motion. So what if I say that when I look inside of this t, what if I say that when I look inside of this t, I can neglect both the minus and the transverse components and use an approximate k, which only has a plus component. And now when I use this k plus, I'm assuming that I've averaged out all of the minus and transverse momenta. Okay, and so if I don't have a k perp here, then I have both the minus and the transverse components inside of this bracketed region, and neither of them are touching that t, that capital T. Okay, well, what you get should be obvious now. The same as what we did up here, but now if I integrate over d2k vector, then I'm going to be integrating over only this exponential part. That's going to give me a delta function that sets yt equal to 0, or yx and y both equal to 0, gives me another 2 powers of 2 pi. And so the end result is that I'm going to end up setting yt equal to 0, getting yt equal to 0 here, and getting different power of 2 pi. So just do that and you get this expression. Note that both the y plus and the yt components are now 0. And this parton density only depends on the light cone plus direction, the light cone plus momentum fraction x. And this is by far the most standard definition that you will see in both textbooks, papers, whatever, for the basic parton density, the basic unpolarized parton density. And again, to see an example of it in a textbook, I reference columns equation 6.31 here. So you can compare what I've written here with what is in at least one textbook. And note that I've put standard up here because this really is the most basic parton density. Now, in terms of notation, what you might see is that you have subscripts. If we have multiple flavors of quark, okay, then we'd have to put flavor F index on the quark fields. And we might also want to say what type of target hadron we're talking about. So we would say flavor inside of P. Okay, so this is basically the end of what I want to say about the basic definition. I've given a much more detailed build up to this basic definition than what you usually see in a textbook, but I hope it's useful. Some things that I haven't done that would maybe help. These are going to be exercises that I leave for you. So it might be worthwhile to actually set up a particular state. You could take the target to be some kind of meson, like make it a very simple one, like say phi, so write it as an S and an S bar, and construct explicit wave packets and actually write down what the parton density in this free theory model would look like, okay? Writing down explicit examples can be helpful. I did everything for a fermion, because I'm thinking about quarks. You can do the same set of steps for a scalar parton, and that can be instructive. You can compare what you expect from a scalar quark versus a fermion quark in, say, deep inelastic scattering. So it's useful to have the expression for a parton density for a scalar. And in principle, it should actually be somewhat simpler because, well, it's a scalar. So you might try going through all the steps that I've just done in the last 3 lectures, but for a scalar particle. I've also not accounted for polarization, the polarization of these objects. The same steps can be applied if you keep in track of polarization. So you might try doing that as well. So those are just some suggestions. Now, what do we have to do next? Well, of course, ultimately, we need to turn on interactions. So dealing with parton densities in an interacting field theory, of course, is much more complicated. And in fact, I started out saying that the discussion I was going to give was maybe not totally rigorous. And part of that is because I've relied very heavily on the properties of a free field theory. If you look back, I relied on that a lot. So what happens when you turn on interactions? Well, you have to think what field is the relevant one to work with, because if you have, say, renormalized fields, then you don't have the same commutation relations, right? We relied very heavily on the commutation relations for the number density interpretation. So you might think about that. When I turn on interesting interactions, I tend to get UV divergences, the very ones that Feynman was talking about. Ultimately, we'd like to understand how to actually calculate a parton density in an interacting field theory. So we need to work out Feynman rules for these. I'll try to get to all of these at some point. But just to give you an idea of what's coming, I'll just mention them here. The other thing is, if you look in the Collins textbook, there's a somewhat analogous but very different development of the definition using light cone quantization. I would suggest to read that. It's good to see the discussion coming from different angles and compare them. Okay, but we have finally gotten the definition we were looking for. That's here. So I think we can stop for now and pick up next time.